All right, the last unit, chapters 9, 10, and 11. 9 is fairly short. I think it's only 3 lessons, if I remember correctly. So we'll be done this one middle of next week. So we're going to look at what a rational function is, and then we'll look at doing some transformations on these using the same principles that we've been using all along. So we'll graph and analyze and compare rational functions using transformations. We'll do it manually as well as using technology, and then we'll look at the behavior of the graphs of rational functions near any non-permissive values. So on the right there, any function that can be written in the form f at x equals p at x over q at x, where p at x and q at x are polynomial expressions and q at x can't equal 0. So basically, whenever you have a fraction where there's at least one of the parts of it, either the top or the bottom, being polynomials, meaning they have a variable in them, then you have a rational function. The only stipulation is that the denominator can't equal 0. That's why it says q at x doesn't equal 0. So some examples are y equals 20 over x, or c at n equals 100 plus 2n all over n, or 3x squared plus 4 all over x minus 5. So those are examples of rational functions. You've got a rational expression, meaning a numerator and a denominator, and at least one of those is a polynomial. So the rational function that relates speed to time for a given distance is related to the base function y equals 1 over x by a vertical stretch. The graph of a rational function of the form y equals a over x represents a vertical stretch by a factor of a of the graph of y equals 1 over x, because y equals a over x can be written as y equals a times 1 over x. So graphs of rational functions of the form y equals a over x have two separate branches that approach asymptotes at both x equals 0 and y equals 0. So we'll see that when we start by graphing. Graph the function y equals 1 over x. We'll use a table of values. We'll identify characteristics and talk about the behavior of the function for its non-permissive values. So when I set up my table of values for this, I'm going to do two different tables of values. One where x is positive and one where x is negative. Looking at the function y equals 1 over x, we do have a restriction on x. It can't equal 0 because you can't divide by 0. So let's see what happens as we get close to 0 and then far away from 0. So what happens when x is something like a quarter, and then a half, and then 1, and then 2, and then what about positive 4? What happens to the values of y for these values of x? Well, the first one, when x is a quarter, y will be 1 divided by a quarter, which is the same as 1 times 4 over 1, multiplied by the reciprocal. When x is a quarter, y is positive 4. When x is a half, 1 divided by a half is the same as 1 times 2 over 1. That gives us positive 2. When x is 1, 1 over 1 is 1. When x is 2, 1 over 2 is a half. And when x is 4, 1 over 4 is a quarter. So you can imagine as x gets closer and closer to 0, for example, if x was 1/10, y would be positive 10. If x was 1/100th, then y would be 100. The closer that x gets to 0, the larger y gets. And x can never equal 0, so therefore the y-axis, which is the line x equals 0, is a vertical asymptote. And again, as we start plotting points here, we had the point 1/4, comma 4. We also talked about the fact that the closer that x got to 0, the larger y would get. But it'll never become 0 because 1 divided by something is always something. It'll never be 0. We had the point 1/2, comma 2. We had the point 1, comma 1, 2, comma a half, and then 4, comma a quarter. And as x gets larger and larger, 1 over x will get smaller and smaller. However, it'll always be positive. It'll never be 0. Again, 1 divided by something is always something. It'll never be 0. So because of that, the x-axis is also an asymptote. Y will never be 0. 1 divided by something will always give you a value other than 0. So we're going to have two branches or arms for this graph. The first, where we're in the first quadrant, looking something like that. Right? And our graphs always have arrows on the ends to show that those patterns continue. So that was choosing positive values of x. What about now if we choose negative values of x? So maybe we'll use negative 1/4, negative 1/2, negative 1, negative 2, and let's say negative 4. 1 divided by negative 1/4 will be 1 times negative 4 over 1, which is negative 4. 1 divided by negative a half will be negative 2. 1 divided by negative 1 is negative 1. 1 divided by negative 2 and 1 divided by negative 4. There's our coordinates when x is negative. And once again, no matter how close that x gets to 0, from the left of 0, meaning that the values of x are negative, what happens is that y just keeps getting smaller and smaller. The closer we get to this asymptote from the left, y is going to get smaller and smaller. I've got the point negative 1/4, negative 4, negative a half, negative 1/2, negative 2, negative 1, 1, negative 2, comma, negative a half, negative 4, comma, negative a quarter. This is what this graph will look like. This is what the graph of y equals 1 over x looks like. And whenever we do any type of transformation on a rational function, this will be our base graph. So when we talk about the characteristics here, we have asymptotes. On the line x equals 0, which is the y-axis, and the line y equals 0, which is the x-axis. Because of that, there are no intercepts for this graph. And also, if we were asked to state the domain and range, the domain would be all values of x such that x cannot equal 0, but any other real number is part of the domain. The only difference with the range is that we're talking about the variable y. Y can't equal 0, but y is an element of real numbers. Okay, but that is the base graph of y equals 1 over x. That is the base graph that we'll be starting with for almost all of our rational functions. So we'll be doing transformations of that. So on the next page, what about the graph of y equals 6 over x? As we saw on one of those first pages, this would be the same thing as y equals 6 times 1 over x, which means that we have an a value of positive 6. This graph compared to y equals 1 over x would be vertically stretched by a factor of 6. It will not change the fact that we have asymptotes along the x and the y axes. And let's start with our base graph. And we had a series of points that we graphed, but the one thing that we saw is that the graph went through the point 1, 1 and negative 1, negative 1. That's what the graph of our base function went through. It went through other points as well, but we're going to use these points as our key point. The rest of the graph is just approaching asymptotes. So then for y equals 6 times 1 over x, or 6 over x, you're going to vertically stretch by a factor of 6. All the y values will get multiplied by 6. So this positive 1 will become positive 6. This negative 1 will become negative 6. Be down there somewhere. So this graph will look something like that. And you definitely could find other points if you wanted to on the graph, but it's just a sketch. Note that the domain and range haven't changed. We still have the same restrictions for x and y. The domain and range have not changed. Okay. This next one says sketch the graph of y equals 6 over x minus 2, take away 3. So once again, this is a transformation of y equals 1 over x. So if we compared to y equals 1 over x, again, we've got that same value of a that we had before on the previous question. A equals 6, so that is a vertical stretch by 6. But also, this graph is going to shift to the right 2 units because we have a c value of positive 2. So it's going to shift 2 to the right. And a d value of negative 3, which is going to cause it to shift down 3. Now you might use h and k instead of c and d. It doesn't matter. We've seen both of those variables used for those parameters. But it won't change the fact that it's going to go 2 to the right and 3 down. So this will change our asymptotes. If the whole graph shifts 2 to the right, instead of having the y-axis as an asymptote, that asymptote will go 2 to the right, to the line x equals 2. And also, instead of having the x-axis as an asymptote, this goes down 3 units. So instead of the line y equals 0, it becomes the line y equals negative 3. Now, what will our new graph look like? Well, we saw before that we had 2 points on the original graph, the point 1, comma 1 and the point -1, comma -1. As we just saw in the previous question, when a equals 6, we multiplied all the y values by 6. But now we're going to have a c value of +2 and a d value of -3, so which means we're going to add 2 to all the x values because it's going to go 2 to the right. So the x value becomes 3 and +1. If we go 2 to the right, we're adding x to all the x values. And we're going to subtract 3 from the y values. 6 take away 3, and -6 take away 3 is -9. Right, so the new graph will go through the point 3, comma 3, which is there, and 1, comma -9 that we're going to have to kind of estimate where that will be. This is -4, 5, 6, 7, 8, 9, approximately right there. So this is what our graph will look like. This graph will have an x and a y intercept. So we can find out what those are. But first, let's write the equations of our asymptotes. And remember, they are equations. They have to have a variable. They have to have an equal sign in them. The equation of the horizontal asymptote is the line y equals -3. The equation of the vertical asymptote is the line x equals +2. Our domain will now be all values of x such that x cannot equal +2, but otherwise all real numbers. Our range will be all values of y such that y cannot equal -3, but otherwise all real numbers. And as I said, there are x and y intercepts here. Remember, to find the x-intercept, it's always where y equals 0. So we'll take the equation and we'll let y equal 0. And then you need to solve for x, which would be done by first adding 3 to both sides. Then we'll multiply both sides by x minus 2, same as cross multiplying. And instead of multiplying out the bracket, we can now divide both sides by 3. And then we actually don't need the brackets anymore on the left. When you divide both sides by 3, on the right, 6 divided by 3 is 2. And then add 2 to both sides, you get x equals 4. The x-intercept is the point 4, comma 0. It's a coordinate. You need an x and a y. Our y-intercept is always where x equals 0. So again, we'll take the equation and now we'll let x equals 0. So on the bottom, 0 take away 2 is -2, so it becomes 6 over -2 take away 3, which is -3 take away 3, or -6. The y-intercept is where x is 0, so that's the point 0, comma, -6. Pardon? Yeah. Yep. All right, so we have a different equation here, but it is a transformation of y equals 1 over x. So compared to y equals 1 over x, we've got an a value of 4. So therefore we have a vertical stretch by 4. We have a c value of -1, so the graph is going to shift 1 left. And a d value of +5, so it's going to go up 5. So because the graph goes 1 to the left, your vertical asymptote will be at x equals -1. And because it goes up 5, your horizontal asymptote will be at the line y equals 5. Once again, if we start with the points 1, 1 and -1, -1, we have an a value of 4, so that's going to be a vertical stretch by 4. All the y values will get multiplied by 4. And then the graph will go 1 left, so that's our c value of -1 and our d value of +5. 1 left means we're going to subtract 1 from all of the x values and add 5 to all the y values. So this graph will go through the points 0, 9. So as luck would have it, we found the y-intercept. We're not going to have to figure that part out algebraically. We could definitely do that to check, but in this case, we're going to use our graphing calculator to check our graph. So that's that arm of the graph. The other arm of the graph goes through the point -2, 1, which is right there. If we write the equations of the asymptotes, they are at x equals -1 and y equals +5. Right? You've got to have a variable, you've got to have an equal sign. We've already found the y-intercept, but not the x-intercept. It looks like it's between 0 and -2. But we'll find out exactly where it is by letting y equal 0 in this equation. So 0 will equal 4 over x plus 1 plus 5. So we would subtract the 5 from both sides. We'll get -5 over on the left. Multiply both sides by the x plus 1. And I'm going to divide both sides by the -5. And you'll get -4/5 on the right. And when you subtract 1 from both sides, it'll be -4/5. Take away 1. 1 could be 5/5, so it becomes -4 take away 5, which is -9/5. Or -1 and 4/5. Or -1.8. Like we said, it's between 0 and -2. So this is our x-intercept. -9/5, 0. Our domain, all values of x such that x cannot equal -1 because that's where our asymptote is. And our range all values of y such that y cannot equal +5 because that's where our asymptote is. So let's use our graphing calculator to check this one. So I need to use some brackets here. I need to keep the rational expression part together. So I open bracket for that. 4 is all I have on the top, so I can just leave that as is. But for the denominator of x plus 1, I also have to put that in brackets to keep it together. So close the bracket on the x plus 1, close the bracket on the rational expression, and then we have a +5 on the end. I'll go zoom 6 to set my windows to their standard settings. So that certainly looks close to what we have. Maybe we'll make our y max a little bit larger so we can see more of it. So why don't we make our y max 20, and maybe we'll change our scale to 2 along the y-axis. So let's check the intercepts on our calculator. If we go into trace, it automatically defaults normally to where x is 0. And you can see y equals 9 there. That's what we got for our y-intercept, 0.0, 9. And also, if we want to find the x-intercept, which we found to be -1.8, second function trace, number 5 for intersect. Nope, sorry. Second function trace, number 2 for 0. I'm going to put my left boundary at -3, my right boundary at 0. Try that again. My left boundary at -3. My right boundary, let's use -1. There we get our -1.8 that we got. Okay, so our graph looks correct. And we got the same intercepts that we got manually. All right, we're going to stop there for today. We should work on page 442, questions 1 and 3. I will get some graph paper out in case you want to use some to draw your graphs for these questions. Also, I have the review assignment for